Hello everyone and welcome to Physics Wallah guys. Hope you all are doing well and your preparation is going to up to the mark. See here in the last we are here to have a very interesting and very beautiful course, and in the last class I think we have covered ramp functions. So basically I have covered three elementary functions. One is a step function, other one is a impulse function, and other one is a ramp function. In today's class, we are going to cover a very interesting topic, that is first a real exponential, and then we will cover that is complex exponential also. That is basically we will cover a periodic and non-periodic signals. Okay, so let me first check that my voice is clear to you or not in my mobile. Hello, hello, hello. Hello everyone. I think my voice is clear. Yes. Okay, now I think my voice is clear. So let's start now. Let's start this class. So what we covered in the previous lecture, we said that we have covered that is a ramp function. So we have covered the ramp function, and I have given you some few problems on ramp functions also. Hope you covered that problems. So ramp function is covered, and now in today's class we are going to cover exponential. In which I will cover both, that is a real and complex. So both exponential I will covered. Okay. So how many elementary functions we have covered till now? I think we have covered a step function. We have covered ramp function. And we have covered impulse. Today we will cover exponential. So this I covered today, and I think that this is the enough elementary that we have covered. Okay. Thank you, Amrita. Let's start now. So today's topic is to cover the exponential. Let me write here also. Let's start now. So first of all, we will cover exponential function. And what do you mean by the exponent? See here, consider a x of t. Let's consider xt, which is e to the power alpha t, where alpha belongs to a real number. If you plot this function with respect to alpha, okay, if you plot this function with respect to alpha, then what you will get? Listen carefully. See here. You know that e to the power minus infinitive, e to the power minus infinitive is 1 by e to the power infinitive, which is 1 by infinitive, and hence it is 0. E to the power 0 is 1, and e to the power infinitive is infinitive. Now since alpha is a real number, okay, so when you put minus infinitive here, it becomes a 0, and when you put 0 here, then it will comes to 1, and when you put infinitive, when you put t is equal to infinitive, then it becomes infinitive. So don't you think that I will get this as a function? This is a function that I will get when I plot against a t. So this is t from minus minus infinitive to plus infinitive. This is what my t is. This value is 1. This value is 1. So it is going like this. Exactly in the same fashion, if that is for alpha greater than 0. Okay, let me call this as a 1. Let's take another one. Suppose I am taking second one, xt to be equal to e to the power minus alpha t. What I'm saying is that alpha is now less than 0. If alpha is less than 0, then how will you plot this function? See, you will plot like this. See, when you put minus infinitive here, then just a minute. Okay. Take here. Suppose here we have this function. So when you put minus infinitive on this function, when you put t is equal to minus infinitive, it becomes a plus infinitive. And when you put t is equal to 0, it will becomes a 1. And when you put t is equal to, let's say, infinitive, it becomes a 0. So what I'm saying is that it is a function which is looks like this one. See, it will go in this way. So this is a function. This is at 1. So this is a function e to the power minus alpha t. E to the power minus of alpha t. So that is what of a real exponential when alpha is plotted against this one. But what I am doing is that, see here, this is 2. Let us plot a new function. See here, suppose I have a third. I want xt to be e to the power minus of alpha t times ut. How will you plot this function? E to the power minus of alpha t ut will be, how will you plot this function? Listen carefully. See here, we have this one. See, what is happening? This function e to the power minus of alpha t is now multiplied with ut, yes or no? If this function is multiplied with ut, then see, this is multiplied with ut. Now, what is ut? You know that ut is this one. No? This is ut. Okay. And when you multiply both this function, what you will get? When you multiply both this function, what you will get? You will get, see here, in the first quadrant, in the second quadrant, you will get nothing because it is 0. 0 multiplied with something is 0. But in the first quadrant, you will get the same function back. You will get the same function back here. Means you will get exactly the same thing. Means what I'm saying is that, don't you think that I will get a function which is this? So this is 0. This is 0. Listen carefully. This is 0, okay, till this one, and then it will have a jump at this point, and then it will go on like this. But what is interesting is that, see here, what is interesting is that look at the point of discontinuity present at this point. See here, I have a point of discontinuity present at this point, 0. Okay, so I have a point of discontinuity at 0. You have to take care of. This is what the important point is. Okay, similarly, if I want to plot, let's say fourth one, e to the power alpha t u minus t, what you will get? E to the power alpha t plot, I already plotted this one, and if I multiply it with u minus t, let's say, if I multiply it with u minus t, okay, then I will get this one, and when you multiply both this function, this is u minus t, when you multiply both this function, that what you will get is this one. See, you will get this function. Towards this one. Okay, fine. So this is what my e to the power alpha t u minus t, and again look at the jump that I will have at this point. So I have a jump at this point. Listen carefully. See, look at the jump. And this jump, after that, this function is 0. So what I want to tell you is that, see here, this is the real exponential. This is a real exponential e to the power alpha t. And when e to the power alpha t is multiplied with u minus t, you will have a jump at this 0, and you will have a jump e to the power minus of alpha t. This is multiplied with ut, then you will have a jump at this point. Question is that what is the value at this function, this 0? See here, what is the value at 0? Let's consider this a value to be, see, when you put t is equal to 0, when you put t is equal to, this value is 1. Here also this value is 1. But if there is a jump discontinuity, then this value is not equal to 1, mind it. This value, I told you that at the point of discontinuity, the functional value is a average of value before and after discontinuity. So before discontinuity it is 0, after this 0 plus, the value is 1. So 0 plus 1 by 2, it's 1 by 2. Same here also. Before discontinuity it is 1, after discontinuity it becomes 0. So 0 plus 1 by 2 is nothing but my 1 by 2 again. What I am saying is that this is the point of discontinuity. Here also, if you look at the point of discontinuity, and if this is the function, see here, at this point of discontinuity, the value is equal to 1 by 2. So at 0, the value is 1 by 2. Here also at 0, value is is 1 by 2 because of finite discontinuity. Because of finite discontinuity. Okay, so because of finite discontinuity, this is the value which is 1 by 2. Now my question is that, suppose if someone asks you that what will happen if you add both this function. If you add both this function, listen carefully, if you add both this function, then what you will get? So what I'm doing is that, let's take yes here. What I'm doing is that I'm adding 3 and 4. I'm adding 3 and 4. So what you will get? That is, I'm adding e to the power minus of at into ut plus e to the power at u minus t. If you add both this function, then what you will get? See here. See, the first quadrant, let's take it graphically first. The second quadrant is completely 0 here, but something is present. And here the first quadrant is present, but the first quadrant here is 0. 0 plus something is that thing only. This means that when you add both this function, don't you think that I will get, see here, I will get a function which is this one. See? Definitely I will get a function which is this function. A two-sided umbrella function. This is known as umbrella function. Okay, and what is the value at 0? That is what the interesting point is. At 0, what is the value? What is the value at t is equal to 0? Listen carefully. At t is equal to 0, listen, the value here is, see, I told you here, the value is 1 by 2 and here also 1 by 2. So 1 by 2 will plus 1 by 2 becomes how much? It is 1. 1 by 2 plus 1 by 2 becomes a 1. So what I'm saying is that this is a complete umbrella function. This is a complete umbrella function. But mathematically, I will write like in this way. See, it is a function. It is a function e to the power, let's say, minus at when t is greater than 0. It is e to the power at when t is less than 0. When t is less than 0. See, if you define the mod t, what is mod t? Mod t is t for t greater than 0 and is minus t for t less than 0 and is 0 at t equal to 0. That's what the mod t is. So if I'm saying that t greater than 0, it is e to the power minus of at. At t less than 0, see, minus t, minus of minus t becomes a what? Positive. And at t is equal to 0, this value is nothing but my 1. So don't you think that I can write this as e to the power minus a mod t? Question is that, will it define according to my definition? See, mod t, if I am taking t to be positive, it is e to the power minus of at. Listen carefully. T positive, this is t. For t negative, when t is negative, then t becomes minus t and minus minus becomes a plus e to the power at. What will happen at t is equal to 0? That's what the point is. At t is equal to 0, this complete function is 1. So look, this is having a 1. So this is nothing but my mod t, okay, and it's a very, very interesting function. Okay. Forgive me. So this is nothing but my e to the power minus of a mod t. So it is a very, very important umbrella function. Most of the time, while taking the Fourier transform also, while taking the Laplace transform also, we will take a umbrella function. Now what will happen? Listen carefully. This is the umbrella function. So what I said, that e to the power minus of a mod t is basically e to the power minus of at ut plus e to the power at u minus t. Okay, and this is a function. So I will plot this kind of function we have. Now question is that who will decide the umbrella of this function? So this function is, the umbrella of this function is nothing but my, let's say, decided by a or alpha, whatever. See, when I change it to be alpha, listen carefully, alpha it is not a, it's alpha, whatever. A or alpha is the same thing. A, alpha is equal to a. Listen carefully. Let me write this one so that no confusion occur. Okay, no confusion occur. I change the alpha to be equal to a. I change the alpha to be equal to a. Okay, so that's what the point is. Alpha is equal to a. Now who will decide the umbrella of this function? A, what I'm saying is a decides umbrella. What is the meaning? Suppose if you reduce the a to be tending towards 0. Suppose I am tending a to be equal to 0. If a I am approaching towards 0, then the same xt will becomes how much? ut plus u minus t. And you know that ut plus u minus t, hello Vinay, ut plus u minus t is nothing but my equal to 1. So what I am saying is that ut plus u minus t is equal to 1. So if I put a tending towards 0, then I will get this function. See, I will get a very interesting this function. Okay, yes, I will get this function. So if this is when a is equal to, this is when a is equal to 0. And now if you increase the values of a, so you will get either this one or this one, or this one, depending on the values of a. So let us call this as a a1, a2, a3, a4. So depending on the values of a, you will get the steepness of the curve. You will get the steep curve, either this one or this one, whatever. Let's take a more flat curve, or this one, see, like this, depending on the values of a. So here a4 is greater than a3, is greater than a2, is greater than a1 or a. And in the network, you will come to know that network and control system, this a is basically a time constant, is governed by the factor time constant, mind it, which is RC or L by R, whatever, R by L, L by R, whatever. Okay? Please check. It may be r by l by l, whatever. It is a time constant of function. So time constant is a factor from which the steepness of this curve will be defined. The steepness of this curve will be defined. Okay. So this A is governed by simple RC circuit. For example, the discharging of capacitor. What is discharging charging of capacitor? Example. The discharging of capacitor. Discharging of capacitor is denoted by V naught e to the power minus of T by RC. See, the discharging of capacitor is denoted by V naught e to the power, which is have this nature. Let's say for t greater than 0. So this means that the whole thing you can write it as V naught e to the power minus of T by RC into ut. So what is the A here? What is A here? Here A is, what is A? A is 1 by RC. So if I am saying that A is equal to 0, this means that I am taking RC to be equal to infinitive. So RC, if time constant is very, very large, RC is very, very large, then the curve is exactly flat. Or if RC is, let's say, phenomenal, then you have a curve depending on the values of RC. So that's what the very, very interesting curve is. Now what I'm doing is listen carefully. Instead of adding both this function, I'm subtracting this function. So let's make a curve. Suppose I have x of t, which is e to the power minus of at ut, x of t e to the power minus of at ut minus e to the power at u minus t, minus e to the power at u minus t. So what curve that you will get? Listen carefully. What curve you will get? See, surely you will get this function. Listen carefully. You will get this, and then what you will get? You will get the reflection of this. See what you will get? You will get the reflection. Means this curve, instead of start with a plus 1, this will have a minus 1. So what I'm saying is that I will get this one. So this is minus 1 and that is plus 1. So what this is? This is the minus of e to the power at u minus t. And what this is? It is e to the power minus of at ut. E to the power minus of at ut. Okay. Now the point is, listen carefully. Now the point is that if I put now a tending to 0, now if I put x of t with a tending towards 0, then don't you think that I will get, see here, I will get a function which is what? See, if I put a tending towards 0, then this becomes a ut and this becomes a u minus t. So this becomes a what? This becomes a this function, and this becomes a this function. So this is 1 minus 1 and that is 1. And I told you that this is a very, very famous function which is basically a signum t. So look how we proceed our journey from the real exponential to signum function. So what is signum function? signum function is e to the power minus of at ut minus e to the power at u minus t with a tending towards 0. With a tending towards 0. Very simple. E to the power minus of at ut minus e to the power at u minus t with a tending towards 0. That's what the signum function means. Okay, and this can be also written as ut minus u minus t. See, it is the ut and minus of u minus t. This is u minus t is this function, so you just reflect this function. But I know that what is 1? What is 1? 1 is ut plus u minus t. So this means that u minus t from this, I can write it to be 1 minus of ut. And when you substitute this u minus t here, I will get ut minus 1 minus of ut. So that I will get this signum t as 2 ut minus 1. So let's summarize. Signum t can be written as, first, e to the power minus at ut minus e to the power at u minus t with a tending towards 0. Number 1. Number 2, ut minus u minus t. And number 3, 2 ut minus 1. This is what a signum representation is. These are the 3 representation of a general signum function. So this is the 3 representation of a general signum function. Okay. This one. Fine. So this is the general representation of signum function. So let's revise what we have covered. We started our journey from a real exponential, both the side, e to the power alpha t and e to the power minus of alpha t, like this. Then what we did is that we multiplied e to the power alpha t with ut and e to the power alpha minus alpha t with, e to the power alpha t with nothing but my u minus t. This is u minus t. And multiplied e to the power minus alpha t with ut. So that I get this function. This is e to the power minus alpha t ut. So it exists only on the first quadrant. E to the power alpha t u minus t, it exists only on the second quadrant. What is the important thing is that here both have a point of decimality at t is equal to 0. So the value is not equal to 1, but the value is equal to half. So when you add both this function, you will get this a very beautiful umbrella function. And this umbrella function, when you combine, then I can represent in terms of mod. By using the definition of mod, I can represent it in terms of mod. So this is e to the power minus of a mod t, where alpha is replaced by a. Just for sake of my convenience, I replace it by a. So e to the power minus of a alpha t is this one. Okay, and this is the umbrella function. And here I represented that umbrella of this function, means steepness of this function is represented by a. If a is equal to 0, you will have a flat function, which is 1. But as you increase the values of a, then the a will nothing but the steepness of this curve comes into the picture. And what is a? Basically a is nothing but a time constant. A is just a time constant. So it may be RC, it may be L by R or R by L, whatever, but the time constant will decide that whether the curve is this one or that one, whatever. Then what I have said, that instead of, listen carefully, instead of taking this way, what I'm doing is that I subtract the second quadrant completely. So if I subtract the second quadrant, then I will get this one. See, completely reflected this function. And now if I put a tending towards 0, then this becomes a flat and this becomes a flat, and I have this function. Okay, I have this function, and this is a very popular function. I told you in the last classes where I have covered the stuff function. Yes, this is the function which is known as signum t, sign of a function. So I have now three representation of a signum function. One is this one. This is just a ut minus u minus t, and since u minus t can be written in this way also, so by manipulation I can write this as a 2ut minus 1. So this is the whole thing, that is the journey from real exponential to signum function I have made in half an hour or 40 minutes. Now let's come to another one. Now let's come to today's topic, that is the characteristics of a signal. Now that is a story when, when, okay, this a belongs to a real number. But what if a becomes a complex function? What if a becomes a complex function? That's one of the very interesting story that we have to cover. Yes, let's take. Give me just a moment. Let's take now. Okay. So now let's talk about a complex exponential function. Suppose, what I'm saying is that, suppose I have x of t as equal to, okay, r e to the power j theta. R e to the power j theta. Let's consider a very interesting function. Where I am taking, for my convenience, assume r to be equal to 1 and theta I'm assuming to be equal to omega t, so that this function becomes e to the power j omega t. Now this time let's see here, look at this function, look at this representation. If I denote it by alpha, here alpha is j omega. This time I'm assuming this to be a complex function. This time I'm assuming this to be a complex function. It's a complex number, yes or no? Where omega is angular frequency. What do you mean by angular frequency? I am covering in just a moment, but let's take it as a granted. Angular frequency in radian per second. What's the meaning of that? We will see in the moment. Hello, Praditya. So it actually is over j omega t. Now what I want to tell you is that, see here, don't you think that this function will repeat after a certain point of time? After some t, this function will be exactly same thing. If a function, if a particular thing repeats after some time, some finite time, then we will say that the particular function is periodic in nature. For example, let's consider a clock. See here, suppose I have a clock, okay, in which I have a, let's say, let's consider I have a hands let's consider this as a clock. Okay, what I want to say is that, see here, if this is the, let's say, a center of this clock, then I have a three hand. One is a, this is a R hand, that is the minute hand, and this is second hand. This is second hand. So what I want to say is that, listen carefully, every hand will come to the same point after certain time. For example, if we talk about the periodicity of the minute hand, then minute hand, okay, minute hand will come to the same position after 60 minute, you will say. Yes or no? And this R hand will come after 60 minutes, it will come into the same position. This R hand will come to the same position after 12 hours. So R hand have 12 hours, or you will say 12 into 60 minutes. It will come into the same position. And what about the second hand? The second hand will come at the same position. Second hand will come after 60 seconds. So let's talk about, it is 60 into 60 seconds. If second is the lowest unit I have, then I have the periodicity of 60 into 60 seconds of minute hand, 12 into 60 of R hand, and second hand has a periodicity of 60 seconds. This is the minimum period. This is the minimum time after which they comes into the same position. Let's mark this position as A, and let's mark this position as a B, and let's mark this position as a C. Whatever be the position it will be, it will means whatever be the present position is, they will come into the same position after definitely this much of seconds. If I'm talking in seconds, you will talk in the minutes also, you may talk in the hour also, whatever. So that's what the time after which they repeat itself. Okay, after which they repeat itself. Similarly, we have a periodicity of years. Okay, from January, after 12 months, a next year will come into the picture. Similarly, in our universe, many things, infinite things are there which are periodic in nature. A circle, this is a question of a circle. Circle is that is a figure which repeats after a certain set of time. Okay, because circle, in just a moment I will tell you that circle is nothing but a combination of sine and cosine according to the Euler's formula. So if I am saying that I have a particular circle, then a circle will nothing but repeats after a certain amount of time. Let's see now. Okay, fine. So what is the definition for periodic signals? See, a signal is periodic if xt is equal to x of t plus capital T. A signal xt is periodic if xt is equal to x of t plus capital T, where capital T is what? Is a minimum fundamental period after which signal repeat. Is a minimum fundamental period after which signal repeat. What I am saying is that, see here, Suppose I have e to the power j omega t. It is e to the power j omega t plus capital T. It has to be there. Then only it will repeat. So let us take this one. It is e to the power j omega t into e to the power j omega capital T. So if you want that it is equal to e to the power j omega t, okay, then this should be equal to 1. Has to be equal to 1. Okay, this has to be equal to 1. Now this is a circular motion, and you know that you have covered in your maths that this circular motion can be written as e to the power j theta is cos theta plus j sin theta, right? E to the power j theta is cos theta plus j sin theta, or e to the power minus j theta, e to the power minus j theta is cos theta minus j sin theta. Cos theta minus j sin theta. So what I am saying is that, see here, that is what I am saying is that a particular circular motion will lead to sine and cosine. And how you can see practically also. See, this, for example, is a circle. Okay, and let's take a let's say this, and suppose if this circle, the axis of the circle, I am taking it as a reference, okay, and these are the 2 points. Taking it as a reference, and these are the 2 points we have. One is this, and other one is this. Okay, then suppose this circular motion, if projected into the linear motion, if this circular motion projected into the linear motion, then the whole thing can be that is made in this way. See, let's take 2 more points. One is this one, and one is this one. Okay, so what I am saying is that, see here, if suppose I have to open, this motion, open this circular motion into this linear motion, then let's mark the point here. Let's mark this as A, this is as a B, this point as a C, this point as a D, and this point as a E, this is as a F, this is as a G, this is as a H, and suppose go back to A, then what you will traverse, if suppose there is a runner which is running on the circular motion, and if suppose this circular motion is projected in the linear motion, then what you will project? I'm starting from A here, then I start with, when it is A, it starts A here, here. When it's B, it starts from B here. When it is C, it's C here. At D, again it comes to here. And when E, I have E here. When F, I have F here. And when G, I have G here. Okay, and so on. And I have H here. And it will go like this. Like this. Forgive my drawing. So what you will get is this one, see? This kind of function we will get. Okay. So what I am saying is that, see here, this is a perfect cosine wave, a sine wave, if I start from here. If I go from here, see, if I go from here, then I will get a sure sine function. Like this. This kind of function I will get. Forgive my drawing, you may traverse the point. I just want to tell you what is the meaning of this equation. See, this equation says that a circular motion will lead to sine and cosine. And what is the phase difference between these two? See, I have started this point as A and this point as a C. So what is the phase difference? The phase difference ideally is 90 degree. That's what the meaning, that cos and sine are 90 degrees of each other. So cos is 90 degree ahead of sine. That's what the meaning here. Okay, so just come to this picture, this one. See here, e to the power j omega t, I can write this as e to the power j omega t. I can write this as cos of omega t plus j sine omega t. Now tell me, what should be the minimum omega t? What should be the minimum omega t so that this value be equal to 1? Why it should not be equal to 0? Because if omega t is equal to 0, then omega is a speed, it will never be equal to 0. T becomes a 0. T is a minimum fundamental period but not equal to 0, mind it. T is a minimum fundamental period but not equal to 0. You must have some t. What I'm saying is that let's consider omega t to be equal to 2 pi. If you put here 2 pi, then cos 2 pi becomes a 1 and sin n pi, you know, that is equal to 0. So this becomes a 0 and hence this becomes a 1. Though it becomes a 1 after 4 pi also, but it should be minimum, na? It should be minimum. So it is not equal to 4 pi. It's not equal to 6 pi. It's not equal to 8 pi. So what I'm saying is that this should be equal to 2 pi. So this gives me a t to be equal to 2 pi by omega. And that is one of the most important expression I have. And hence what I'm saying is that if this t, if I put here capital T to be 2 pi by omega, if I put t is equal to 2 pi by omega, then this function will repeat itself. Okay, so when I say that I have an x of t equal to, let's say, e to the power j omega t or e to the power minus j omega t, or more precisely sine omega t or cos omega t, or in this way a sine omega t plus phi or a cos omega t plus phi. For all these functions, mind it, for all these functions, the capital T comes out to be 2 pi by omega. The capital T is 2 pi by omega. This is what one of the most important point we have. Is it clear? So whenever you have a function, whenever you have a representation, for example, in either in this form, then the capital T comes out to be 2 pi by omega. Is it clear to you? This is a very important point. Now, two things you have to take care of. For a periodic signals, they must be everlasting in nature. What is the meaning of that? So let's take a remark. 1. Periodic signals are everlasting. What is the meaning of everlasting? Everlasting means the existence must be from minus infinity to plus infinity. So if suppose I have cos of 3t, then it is a periodic, because omega is 3 and hence t is 2 pi by 3. No problem. This is periodic. But when I say that cos 3t ut, then it is a non-periodic function. It's purely non-periodic. It's a non-periodic. Why non-periodic? Because it exists from 0 to infinity. It exists from 0 to infinity. So that's all the meaning, that whenever I say that periodic function I have, then it must exist from minus infinity to plus infinity. That's what the meaning of a periodic nature of a function is. That's what the one thing. Second thing is that, see here, let's come to the second thing. Second remark is that its amplitude variation is same for each period. What is the meaning? For example, if I am saying that I have cos 3t, then you know that what is cos 3t? The cos 3t is this function, see here. Like this. So forgive my drawing, if you take the amplitude here, okay, it's a shame. Okay, so if you take the amplitude from here to here or here to here, the variation is exactly same. The variation is exactly same. See, whatever the variation, any amplitude, any period if you take, the variation is exactly same. It will not change. But let's consider e to the power minus of alpha t sin 2t. So how will you make this function? See here, first make e to the power minus of alpha t. Just now, today's class we have made e to the power minus of alpha t is this kind of function. Okay, and sine function will have two maximum values. One is a plus 1, another one is a minus 1. So this means that let's make a minus 1 like this, and in between you have a sine curve like this, and so on. So this is the damped oscillation function. And look at this one. The amplitude is constantly decreasing. So this means that if you consider this to this or this to this, if you consider these two functions from here to here or from here to here, then they are not same. So this means that this is non-periodic. Okay. So this function is purely non-periodic function. The amplitude variation must be same for each and every period. Okay, fine. So these are the two remarks that you have to take care of. Okay. First thing is that the periodic signals must be everlasting in nature. So they should exist from minus infinitive to plus infinitive. And another thing is that they exist, that's the amplitude variation is same for each and every period. Okay, now let's consider, suppose I have x of t, which is a combination of x1t plus x2t plus x3t and plus so on and so forth. And each are periodic with a period of t1, let's say t2, let's say t3, and so on. And they all have a frequency also. Let's say omega 1, and let's say omega 2, and let's say omega 3, like this. Question is that whether this combination is periodic or not. Whether this combination is periodic or not. That's what the point is. If this combination is periodic, then what should be the fundamental period of combined signal x of t? So see here whether xt is periodic. If yes, what is t? This is the question that we have to address. Let's do it. See, how will you check that whether this is periodic or not? Listen carefully. This is periodic if xt is periodic if t1 by t2 or t1 by t3 or t1 by t4 and so on is a rational number. Is a rational number. T1 by T2 or T1 by T3, T1 by T4 is a rational number. Where what is rational number? What do you mean by rational number? It is in the form of P by Q form, where P comma Q belongs to integer and Q should not be equal to 0. That's what the definition of this one. So for example, let's consider okay. Let's consider example. Suppose I have an x of t which is equal to, let's say, sine 3 pi t plus cos 2t. Let's consider this one, x1t, and x2t is sine 3t plus sine 60 plus sine 10t, and let's consider x3t as cos 9 pi t plus cos 20 pi t plus cos 60 pi t plus pi by 4. Tell me, out of these three, which one is periodic? Let's consider the T1 here. Let's find out the T1 here. T1 is 2 pi by 3 pi. This means that it is 2 by 3. Let's consider T2. T2 is 2 pi by 2 and this comes out to be pi. What is T1 by T2? What is T1 by T2? T1 by T2 is 2 by 3 by pi or 2 by 3 pi, which is not a rational number. Irrational. Irrational. Which is irrational and hence it is non-periodic. But let's check out this one. See, if you consider T1, it is 2 pi by 3. It is T2, it is 2 pi by 6. T3, 2 pi by 10. What is T1 by T2? T1 by T2 is 2 pi by 3 by 2 pi by 6 or comes out to be 2 by 1. What is T1 by T3? T1 by T3 is 10 by 3. And both are a perfect rational number and hence this is periodic. Perfect periodic. What about this one? See here, T1 is 2 pi by 9 pi, 2 by 9. T2 is 2 pi by 10 pi, 20 pi, sorry, which is 1 by 10. And 2 pi by 60 pi, which is 1 by 30. Look, T1, T2, T3 itself is a rational number. So their ratio will also be a rational number and hence it is also a periodic. So what is the important thing that you have to draw from these three examples? See, this is a combination of pi and without pi. This is the combination of pi and without pi and hence this is a non-periodic function. This is a combination of without pi. This is a combination of with pi. So combination of either pi or without means pi and without pi will always be non-periodic. But if there is a sole combination of pi or without pi, then it comes out to be periodic only because they comes out to be a rational number. Now this is how I check that whether the function is periodic or not in continuous time. Okay, in continuous time. Okay, fine. Yes. So this means that whether this function is actually periodic or not. So I have told you by a one example. Now let's check out what I'm saying is, see here, let's check out that what is a period. What is a period? What is period? So period is take LCM of T1, T2, T3 up to so on, and the LCM is period of xt. So this is the period of x of t, or take GCD of omega 1, omega 2, omega 3, up to omega n, and that GCD I'm calling it as a omega naught. I'm calling as a fundamental frequency. Fundamental frequency, and T is 2 pi over omega naught. 2 pi over, hello Anurag, 2 pi over omega naught. So total T is 2 pi over omega naught. These are the two methods from which you can find out the period of this function. For example, let's consider this one. So T1 comes out to be, this is non-periodic, I know, that comes out to be this one. T1 is 2 pi by 3, 2 pi by 6, 2 pi by 10. Suppose, find out the period of this one. Find out the period of this one. Easily you can find out. See here. T1 was 2 pi by 3, 2 pi by 6, and 2 pi by 10. Let's find out the common period of this function. So you have to take the LCM. See, whenever you have a factor, let's say P1 by Q1, P2 by Q2, P3 by Q3, and so on, then to find out the LCM, what you have to do? It is the LCM of P1, P2, P3 divided by HCF, highest common factor of Q1, Q2, Q3. Okay. But in reduced form. Mind it that this should be 2 pi by 3. So it is a pi by 3. It is pi by 5. Remove the common factor first. Now what is the LCM of? Two pi, pi and pi. And what is the SCF of? 3, 3, 5. See, the SCF is 1 because the highest common factor is the factor which divided by integer set of value is 1. 1 3 is 3, 1 3 is 3, 1 5 is 5. Easily we can find out the highest common factor. What about the LCM? LCM is, I think it is a pi. So this should be a pi. Let's check it by, or 2 pi. Let's see. Easily you can find out 2 pi. It is 2 1 1 2 pi. This should be 2 pi. So this is the period is 2 pi. Easily you can find out this period is 2 pi. Let's check it by omega method. So what is the, this is from T method. From T method. Okay. And let's find out through the omega method. So sin 3t, sin 60, sin 10t. So it was sin 3t plus sin 60 plus sin 10t. Okay. What is omega 1? 3. Omega 2 is 6 and omega 3 is 10. Tell me what is the highest factor which divided by integer set of values? To each of these omega, it is 1. 1 3 is 3, 1 6 is 6, 1 10 is 10. No other values. This means that this omega naught comes out to be 1 and t comes out to be 2 pi by 1, which is 2 pi. Exactly the same thing. No? Exactly the same thing. So by finding the LCM of capital T, by finding the LCM of capital T and by finding the highest common factor of omega, easily you can find. For example, this one, let's take this one. Cos 9 pi t plus cos 20 pi t plus cos 60 pi t plus pi by 4. Let's take an example 1. Example, again, suppose I have a cos 10 pi t plus cos 20 pi t plus cos let's say 5 pi by 3 t plus pi by 4. I want to go by what? Omega method. So let's take a omega 1. Omega 1 is 10 pi, omega 2 is 20 pi, and omega 3 is 5 pi by 3. Let's find out the GCD. So it is a GCD of 5 pi, 20 pi, and 10 pi divided by GCD of or divided by LCM of 1, 1, and 3, because it is 1, 1. Now this time look at this one. What is the highest value on this numerator that I will take, so that it will divide it by integer set of values? So that it will divide it by integer set of values, and this value is 5 pi, I think so. See, 5 pi. This is 5 pi. Why? Because 5 pi 1 ja 5 pi, 5 pi 4 ja 20 pi, 5 pi 2 ja is 10 pi. And what is the LCM? LCM is 3. So the omega naught, that's what the omega naught is. Omega naught comes out to be 5 pi over 3. So T would be 2 pi by 5 pi by 3, or comes out to be 6 by. So this is the fundamental period of this function. This is the fundamental period. T is the fundamental. I am giving you the homework that prove the same T by using a LCM method. Take T1 first, find out T1, T2, T3, and take the LCM, and you will get the same answer, 6 by 5. So that is what a periodicity of continuous time function, though I have not covered a discrete time periodicity. Okay, so let's take what is covered till now. Let's do it. So we have covered a real exponential, and we have covered a complex exponential also. And we have covered periodicity. So these are the three things. These are the three things that we have covered in today's class. And discrete time periodicity. Next class will be discrete periodicity. Discrete periodicity, and we will cover the power and energy signal also. If time permits, we will start. Okay. So this is what we have covered till now, and with this, thank you very much, guys. If you have a doubt, then you will surely ask the doubt. Okay, I am here for 10 seconds, and thank you very much. Thank you.